Hello everybody, this is Daniel Solomon from Tel Aviv University and I'm going to talk about margin pointers, which is a new technique for safe memory reclamation in concurrent search data structures. This is joint work with Adam Morrison, also from Tel Aviv University. First, let's talk about our model. We're in the field of concurrent data structures, which are data structures whose data is shared and accessible by several threads at the same time. We concentrate on non-blocking or lock-free data structures, which are implemented without locks and require atomic synchronization instructions such as compare and swap and fetch and add. Lock-free algorithms also guarantee that if the program will make enough steps, at least one thread will complete an operation, regardless the state of the other threads, even if they have crashed or stalled. Lock-free data structures face a safe memory reclamation challenge. They need to ensure that a node will not be reclaimed if there exists a thread that is accessing it or might access it in the future. In a low-level environment such as C or C++, without any garbage collection, the SMR problem is handled by a safe memory reclamation scheme. Instead of freeing a removed node from the data structure, it is retired, and the SMR scheme reclaims a retired node once no thread has a reference to it. Let's see a simple example that illustrates the SMR problem. So here we have a linked list, and we have a thread that has a reference to 20, and it stalls. Another thread wants to remove 20, it accesses 10, and then 20, and then it unlinks 20 from the data structure. The next thing it wants to do is to free 20, but then if T1 wakes up, it can still access 20 since it holds the reference to it. So 20 cannot be freed since T1 might access it in the future. An SMR scheme has two goals. First, to impose a low runtime overhead of the client data structure. Second, to minimize the number of nodes that have been retired but not yet reclaimed. We refer these nodes as wasted memory, since they have been removed from the data structure, but their memory cannot be reclaimed or reused. We will now briefly describe the state-of-the-art in SMR schemes and its limitations. A pointer-based reclamation scheme protects specific nodes from being reclaimed. Each thread maintains a set of pointer protection variables, which are generally called hazard pointers. It uses hazard pointers to announce any node that it has a local reference to. These nodes are considered protected, and for correctness, all writes to hazard pointers must be visible immediately to all other threads. It requires issuing a costly memory fence instruction. So if a thread searches for the key 20, it must first protect it with the hazard pointer. If another thread tries to remove 20 at the same time, it cannot reclaim its memory since it is aware that another thread has a hazard pointer to it. And the node can be reclaimed only if there is no pointer protection variable which protects it. Each thread can block nodes from reclamation up to the number of hazard pointers it owns. Therefore, the wasted memory is at most t times the number of hazard pointers. To sum up, HP imposes a high runtime overhead due to the expensive per-node memory fences, but it provides a predetermined bound on the wasted memory. Another type of safe memory reclamation schemes is epoch-based reclamation. EPR schemes impose lower runtime overhead than HP, but at the cost of not bounding the wasted memory. In EPR, the protection is done in resolution of epochs. There is a global monotonically increasing epoch, and each thread has a local epoch that represents the current epoch it is operating on. Before starting an operation, a thread must announce that it is starting working on a specific epoch, which must be visible to all other threads immediately. It requires issuing a single memory fence per operation. The global epoch is advanced each time reaching a quiescent state, which is defined by a time that all threads lost their references to the data structure at least once. A retired node will be reclaimed only when the global epoch has advanced enough time since its retirement time. Okay, so let's see an example. Here we have a list and a thread starts an operation on it. It means that all nodes are protected at once. Then if it suddenly stalls, any retired node cannot be reclaimed since all nodes are protected. And only when it completes its operation, then the protection is released and retired node can be reclaimed. It means that a mid-operation stalled thread prevents memory reclamation indefinitely, so the wasted memory is unbounded. Okay, so let's sum up. Epoch-based reclamation imposes low runtime overhead due to a single memory frame's per operation, but it cannot bound the wasted memory. Robust epoch-based reclamation are EBR schemes that are robust, which means that memory reclamation is not blocked indefinitely. Hazard eras and interval-based reclamation are two examples of robust EBR schemes. They both track the lifetime of each node from its creation to its retirement, and they use this lifetime to infer whether a retired node may be accessed by a stalled thread. So for example, if we got a list and a thread is operating on it, and it suddenly stalls, if we connect 40 to the list, the scheme can identify that the 40's lifetime does not intersect with the working epoch of the stalled thread, and therefore it cannot hold a reference to 40. So 40 can be reclaimed safely. The observation that motivates our work is that robustness by itself is not a strong guarantee. It still allows the wasted memory grow arbitrarily large. For example, the data structure can grow arbitrarily large before a thread starts an operation on it, and then it stalls. If another thread removes all the nodes from the data structure, new linked nodes can be reclaimed, but all the old nodes cannot be reclaimed since the stalled thread protects them all. So while it is true that robustness guarantees bound on wasted memory, the problem with that bound is that it is not predetermined and fixed like in other pointers, and as we've seen, it can grow as large as we want to, potentially up to the size of the available memory. Robust EBR schemes are improving the wasted memory guarantee in general, but they cannot provide a predetermined bound. And to summarize, there is no safe memory reclamation scheme that imposes low runtime overhead while guaranteeing a predetermined bound on wasted memory. This is the exact motivation for our margin pointer scheme that aims to achieve both. Margin pointers is a PBR scheme like other pointers. But while HP protects specific physical nodes, MP protects logical portions of the data structure. This idea allows MP to issue fewer memory fences than HP. HP must protect and fence every single node it visits. In contrast, MP protects an interval of keys, all of which are within a margin or distance from a given key. Because of this interval can protect several nodes, a thread can access multiple nodes without updating any margin pointer record. This significantly reduces the runtime overhead of MP compared to HP. The pointer protection variables of MP are called margin pointers, and for the logical protection we require that the keys will be immutable and totally ordered. Then a margin pointer record on key K actually protects any node that is associated with a key in the range between k minus half m to k plus half m, where m is a configurable constant parameter we call margin. It's worth mentioning that MP can be used with any data structure that is compatible with HP, but it is only efficient on search data structure because of the special way the keys are organized within them. Let's see an example. So here we have a binary search tree, and we configure the margin to be 20, and we are searching for the key 90. We would also like to count the number of memory fences we are issuing, and each time we will place a margin pointer record, we will increase it by 1. So first we want to access the root of the tree. So 50 needs to be protected. We place a protection on 50, and it means that any node with a key between 40 to 60 is protected. So these nodes are protected, and we access 50. 70 is not protected, so we place another protection on 70, and now these nodes are protected as well. We can move to 70. And now notice that 80 is already protected by a previous margin pointer record, so we don't need to place another protection on 80, and we don't need to execute another memory fence. So we move to 80 safely. Now 90 is not protected, so we place a protection on 90, and we can access it safely as well. So overall, we visited 4 nodes, but we placed only 3 margin pointer records. So actually, we placed only, we had to issue only 3 memory fences, in opposed to other pointers in which we would fence 4 times. In the last example, we ignored the chicken and egg problem. How can we place protection on a key K that we don't know its value without accessing the node we are trying to protect? To overcome this, we encode the key in the pointer to the node. So our pointer representation is actually a pair, the node's address and its key. This encoding technique is not so simple, and it raises 3 problems. First, in some key domains, the protection interval contains infinitely many keys, which means that each margin pointer record can block an unbounded number of nodes from being reclaimed. Second, in some key domains, it is not clear or efficient to calculate distance between keys. And lastly, encoding an entire key in a pointer might double its size. And how can they both be updated atomically with a single compare and swap instruction? To solve this, MP uses fixed width integers called indices. Every node is associated with an index, and the index is hidden, which means that the client application is not aware of its existence. In addition, MP enforces that the indices will agree with the key's total order, which means that if a node's key is larger than another, then its index is larger than the other as well. Instead of protecting an interval of keys, the protection is done on indices. And any node whose index is covered by the interval of indices is considered protected. This protection induces interval of integers, which is bounded, and it's also easy to calculate distance between 2 integers. And that solves our first 2 problems. As for the pointer size, we pack both the address and the index of a node in the pointer to it, which keeps it a single memory word that can be updated atomically using a single compare and swap instruction. We rely on the fact that common architectures such as x86 and ARM use only 48 bits of virtual address space. The other bits are reserved and they can be used for packing the index. The final pointer representation in MP is a pair, consists of the node's address and its index. This representation allows protecting a node correctly before accessing it. Importantly, MP doesn't use a static key-to-index mapping. Instead, indices are created at runtime according to the data structure's dynamics, in a way that physically closed nodes will be also logically closed by assigning them indices with close values to each other. MP leverages the behavior of search data structure's insert operation. The insert operation first searches for the correct place to insert a new key. It implicitly maintains a range of possible keys that shrinks for each taken comparison, until it eventually remains with the predecessor and the successor of the key. Since indices must agree with the total order of the keys, the new index, which will be assigned to the node, must be between the predecessor's index and the successor's index. To assign it correctly, MP exports 2 functions, update lower bound and update upper bound, which are called by the client algorithm when it seeks towards higher or lower keys. This way, MP can adjust the endpoints of the index boundaries correctly, and eventually it will assign the average index of the predecessor and the successor of the new key. Since MP maps a large key domain to fixed-width indices, several nodes may be assigned with the same index. We call it a collision. Those collisions can make a single margin pointer record to protect an unbounded number of nodes from reclamation. This is problematic since we want MP to bound the wasted memory. There are two types of collisions. The first one occurs inside the data structure, and it happens when there is not enough space for integer between the index of the predecessor and index of the successor. The second type occurs outside the data structures between retired nodes, and if we repeat this process, we can get an unbounded number of retired nodes with the same index. To solve the index collisions problem, MP protects nodes with colliding indices using HP, and uses EBR ideas to bound the number of protected nodes by a single margin pointer record, even if there is an unbounded number of retired nodes with the same index. Please see the paper for the full details. MP guarantees a predetermined bound on the wasted memory. Each margin pointer record protects M indices. Without collision, each index is associated with at most one node, which means that each thread protects at most the margin size times the number of margin pointer records it owns. However, collisions can happen, and handling them introduces additional factors. But the important point is that all these additional factors are predetermined as well. Now that we are familiar with MP, it is time to define which data structures are compatible with it and how to do such an integration. Since MP can fall back to HP, any HP compatible data structure is also MP compatible data structure, but only such data structure will benefit from the reduced runtime overhead MP imposes. The reason is that MP leverages the search data structures in insert operation for smart index selection, which result in fewer memory fences and hence lower runtime overhead. We applied MP to several data structures: linked list, binary search tree, and skip list. And now I'll present the linked list integration, but it's worth mentioning that the other integrations are similar and require the same amount of effort. First, we use an HP-compatible version of the linked list. Then, for completeness, we must assign indices for sentinel nodes according to the location and what they represent. In the linked list, we got the head and the tail, representing the lowest and highest keys available. So we assign them the minimal index and the maximal index respectively. So here is how an empty linked list looks like. The remaining modification is crucial for the index creation process. The client algorithm should update MP when it seeks towards higher or lower keys. It does it by using the functions update upper bound and update lower bound that MP exposes. Each comparison, the relevant function is called with the compared node. Since the list is in ascending order, each visited node actually updates the lower bound of the search interval, which means that the lower bound of the indices interval should be updated as well, except for the last visited node, which its key is larger or equal to the target key. So in this case, the upper bound of the indices interval should be updated. Okay, so now this linked list implementation is finally compatible with MP, and it can use MP as its safe memory reclamation scheme and enjoys its profits. Okay, so now I'll briefly show you some of our experimental results comparing margin pointers to other safe memory reclamation schemes. First, let's talk about the setup. We configured margin pointers to use 32 bits indices and a margin of size 2 in power 20. We compared it to the tagged version of an interval-based reclamation, Azad eras, and other pointers. For client algorithms, we use two search concurrent data structures, skip list and NM binary search tree. And our experiment ran on a machine with a total of 88 hardware threads. We use integers key space between 0 to 1 million, and in each micro benchmark we increased the number of threads. We started from 1 up to 100. Notice that we intentionally exceeded the number of hardware threads, so we can see how context switches and thread stores affect the results. And in each micro benchmark, we started by pre-filling the data structure with 500,000 keys. And then each thread invoked random operation for 5 seconds according to 3 different workloads: read-dominated, write-dominated, and read-only. Okay, so these are the throughput results of NM binary search tree. We can see that margin pointers outperforms other pointers in all workloads, and it is comparable to the other epoch-based reclamation schemes in the non-read-only workloads, and it even outperforms them when we exceed the number of outer threads. The skip list throughput graphs show similar results, and we also measure the average size of the wasted memory. We can see that only MP and HP show a neglectable amount of wasted memory regardless the number of threads. Finally, we compare the average number of fences per visited node both in MP and HP, and we can see that HP fences as twice as much MP does. So our evaluation takeaways are that first, MP is the best performer in its category. For SMR schemes with predetermined bound or wasted memory, MP outperforms HP consistently. And second, in non-read-only workloads, MP is comparable to other epoch-based reclamation schemes and even outperforms them in some cases while still bounding the wasted memory. And last but not least, MP wastes less memory than epoch-based reclamation schemes, not only in theory, but also in practice. Okay, so now we can fill MP in our comparison table. And for search data structures, MP is the only scheme that provides a predetermined bound on wasted memory and imposes low runtime overhead. However, for non-search data structures, the overhead of MP is similar to HP. So let's wrap it up. We introduced margin pointers, the first safe memory reclamation scheme that guarantees predetermined bound on wasted memory while imposing low runtime overhead. The key idea is that MP protects logical parts of the data structure, as opposed to previous approaches that protected specific physical nodes. And our evaluation shows that MP outperforms HP, and it can even be competitive with state-of-the-art epoch-based approaches. So thank you for listening, and if you are interested in more details, I encourage you to read the paper.